All right, welcome to our next unit, which is all about gases. Now, you think about gases, you think of a smokestack like this one right here that's got some gas coming out of it. You might think of your burner at home that you use to cook your food on. That obviously contains a gas that's being ignited and creating some energy. You might think of even like a neon sign that has gas inside of it. When you shoot electrons through it, it gets excited. So when we talk about gases, what we're talking about is we're talking about things that sometimes can be in a liquid form, but if they have enough energy associated with them, they can turn into a gas. So if you look at the periodic table, there's actually 11 elements that when they are in their elemental form, they are in a gas phase. And if you look at the periodic table, they usually will have a different color associated with them. For example, the periodic table that I have up in my room, up in the front, the red ones are the ones that are gases in their natural state. And a lot of them also are diatomic molecules as well. So for example, hydrogen, again a gas, and then going to the opposite side, you've got nitrogen, N2, you've got O2, you've got F2, you've got Cl2. So those are 5 of your diatomic molecules. Remember that there's also bromine and iodine as well. So there's 5 gases that are elements that are, when they're in their elemental state, they are gases. And then obviously the noble gases, the very last column on the periodic table, those are also always gases. So helium, and then straight down the periodic table. Okay, so today what we're going to do is we're going to be able to describe the properties of gases compared to other physical states. So how does a gas, how is it different from, say, a solid or even a liquid? And then we're also going to use some common units of gas in measuring the pressure and also measuring the temperature, and then we're going to be able to convert between them. So some characteristics of all gases. When you put a gas into a container, it will occupy the entire volume of that container, and it will obviously take the shape of that container as well. Gases are molecules usually that are completely separate from the other molecules that are in there, and so they will not attract each other nor repel each other very much, and what they will do is they will fill up the entire space that they are placed into. They can be highly compressed, but much more than a solid or a liquid can, but they will still have quite a large distance between the molecules when compared to a solid or a liquid. If you do compress a gas enough, it actually will turn back into a liquid. Think about like a propane tank. When you go fill your propane tank and you get, let's say, 5 gallons of propane, that propane will actually be in a liquid form because the pressure is high enough inside that propane tank that you can actually slosh it around a little bit, and you can hear the propane, the liquid propane, moving around in there. Once you release that pressure and you produce a spark or light a match, then the liquid will turn back into a gas, and so you will ignite the gas that is coming out of the tank. And then, as we know as well, gases also have a much lower density. Remember that density is the mass over the volume. Gases tend to have really low masses compared again to liquids and solids, so their densities tend to be a lot lower. So a couple of things that are different about gases is they do occupy the volume and the shape of whatever container they're in. They can be highly compressed. There is a large distance between the molecules, and they do have a much lower density. And then our fourth characteristic of gases is they do mix completely, and they form homogeneous mixtures when they combine with other gases. So an example of that might be something like air. Okay, in the case of air, air is not just, if you look at the periodic table, there's no air up on the periodic table because it's not composed of elements. It's a mixture, it's a homogeneous mixture of gases. It's a mixture of oxygen, it's a mixture of nitrogen, it's a mixture of carbon dioxide, it's a mixture of a whole bunch of different gases. So we know that that a lot of times gases will mix with other gases and form these homogeneous mixtures. Okay, what's the difference between a gas and a vapor? A lot of times you hear about water vapor. So we're going to talk about the difference between those two things. So a gas is something that under normal circumstances, under normal temperature and normal pressure, which we're going to talk a little bit about today, is actually in the gas phase. So for example, helium is a gas because at a normal temperature, around room temperature, and when the pressure isn't very high, helium is still a gas. Whereas a vapor is something that, again, under normal circumstances, under normal temperature and pressure, is either a liquid or a solid. So water at room temperature is a liquid. We don't call it water gas, we call it water vapor, because water does not normally form a gas unless the temperature gets high enough. So under normal temperature and pressure, if it's a liquid or a solid, we call it a vapor when it turns into a gas. Now, let's talk about the pressure of a gas. How much pressure a gas is under is going to have a big effect on how that gas is going to respond. So when a gas has a change in volume, it also experiences a change in its pressure. A good example of that is what you guys do with those water bottles, you know, those little things from Costco. That's a terrible water bottle. But when you take that and it's empty and you squeeze it, what you're doing, so you're compressing it, you're pushing on it and making that smaller, you're changing the volume of that container. And when you make it smaller, what does the pressure do? The pressure goes up. So when the volume changes, so does the pressure. The pressure is the force acting on an object per unit area. So it's the force over the area. Not something you need to necessarily remember, but if you think about it, that's how much, basically the force is how much it's pushing. So how hard, for example, the air inside of here is pushing against the walls per unit area. So when you make the bottle smaller, the force stays the same, but you just made the area smaller. And we know that when you decrease the denominator of a fraction, the answer gets bigger. Now in chemistry, there's 3 different units that we're going to learn in terms of pressure. One of them is, the term is called atmospheres. The abbreviation for that is ATM. ATM does not stand for atom. ATM, anytime you see the letters ATM together, that is a unit of pressure, which was referred to as atmospheres. There's also a unit called millimeters of mercury, and again the abbreviation for that is MN, is millimeters, and then Hg is obviously the symbol for mercury. And then also torr. And again, we'll see. We're going to see all 3 of these here in just a second. Now, what you need to really know is how to convert between one and the other. 1 atmosphere is like regular atmospheric pressure. You don't feel it right now, but there is pressure pushing on your skin right now. The air molecules are hitting your skin and they're creating some pressure. And that 1 atmosphere is about what you feel right now in the air. And that is equal to 760 millimeters of mercury. And basically what that means is mercury, remember, is a liquid metal. And so what you can do is basically you can have a device, it looks much better than this, but more or less it looks kind of like this. And basically what it does is one end will be sealed, and then the air or whatever's in there will push on that mercury. So here's your mercury down in here, and it will push on that. And so what happens is one side, let me see if I can do it a little bit better over here. So basically on one side, if it pushes high enough, the mercury will be higher on this side than it is on this side. And so that difference between the two, it can measure the pressure. How much is it pushing on this right side to cause this left side to go up? And so what we define as the same thing as 1 atmosphere is if that difference is 760 millimeters of mercury. And then obviously you can see that the same thing here is what we use for torr. Now, just as a reference, here in the United States, a lot of times when you blow up tires on your bike or in your car, a lot of times we use pounds per square inch, or what you call PSI. And 1 atmosphere is equal to about 15 PSI. So think about like your car tires. You blow those up to about 35 PSI. or even like if you ride bikes, a bicycle tire might be 50 psi. If you ride a road bike, it might be up to 100 psi. So that would be about 7 atmospheres of pressure if you were at 100 psi, roughly, more or less. Okay, now the reason I made that small is because we're not going to use that. We don't use pounds, we don't use inches in science. That's just to give you a reference. 1 atmosphere is about 15 pounds per square inch. Okay, so here you can see this is a barometer, and then you can see these numbers on the inside, and then down here you can see those millimeters of mercury. And so what this needle is doing is it can move, obviously, in different directions, and it tells you the atmospheric pressure. Like I said, on a normal regular day, your pressure is probably going to be somewhere right around that 760 number. But this needle will move depending on whether a storm is coming in or whether a storm has just left the area. And the air pressure will change based on that, basically on how much air is in the area. And you can see that one of the ways that they measure it is in millimeters of mercury. Another way they measure it, which we aren't actually going to discuss, these big numbers on the outside, see that HPA there? That actually stands for hectopascals, which again is not something we're going to use in this class. So how do we use these pressures? We have 1 atmosphere, we've got these 760 millimeters of mercury, and we've got our 760 torr. So what you might be asked to do is you might be asked to convert from one to the other. So if they ask you to convert 840 torr to atmospheres, a lot of times we feel like if we're at torr and we have to get to atmospheres, we have to go here to here. That is not accurate. If you are at torr and you need to get to atmospheres, what you can do is you can just go directly from torr right to atmospheres using that conversion. Because they're all equal to each other, we can just set one equal to another. So we know that 1 atmosphere is equal to 760 torr. So if that's our conversion and we need to convert, we're going to go 840 torr. Now we want to cancel torr, so we need to put torr on the bottom. Here's my conversion again. So I'm going to put 760 torr on the bottom and what it's equal to on the top. And so now I can take my calculator and I can say 840 divided by 760. I don't need to multiply by 1. Now I notice here I've only got 2 significant figures. There's no decimal point at the end. So there's only 2 significant figures. So I'm going to report my answer as 1.1 atmosphere. So that is a conversion to go from torr to atmospheres. Okay, and that's something that you absolutely have to be able to do. Okay, here's another example. So this first one is 1.1 atmosphere. Here we're going to convert atmospheres to millimeters of mercury. So here's our conversion factor. So we've got 0.954 atm. Now we know our conversion is 1 atmosphere equals 760 millimeters of mercury. So to cancel atmospheres, it's got to go on the bottom. So 1 atmosphere on the bottom, 760 millimeters of mercury on the top. Atmospheres are going to cancel. So now we're going to take 0.954. We're going to multiply by 760. And again, 3 significant figures. Remember, don't use these with your significant figures. We're just using the numbers that they give us in the problem. And I get an answer of 725. And do the math yourself here. Make sure that you're getting the same answer as I am. I very easily could be making a calculator mistake and getting the wrong answer. But you should get somewhere right around 725 millimeters of mercury. So to convert between one pressure unit and another, you simply place the pressure unit that you want to cancel on the bottom and the one they're asking you for on the top. And then you're going to cancel the units that you've already used, and then you're going to end up with the unit that they're asking you for. Okay, here's one more example. We've got 147.2 torr. So again, remember 760 torr is pretty much what you feel every day of your life. Okay, so 147 torr is actually really, really low. So that's a pretty small amount of pressure. But we want to convert that to millimeters of mercury. So in this case, now we can see those are our two units there. They are exactly the same. So we could write the whole thing out, and we could say 147.2 torr, and then we do the whole steps. 760 torr, 760 millimeters of mercury, and then hopefully you see that the 760s cancel, and it actually ends up being the exact same answer, 147.2 millimeters of mercury. Okay, and if you can do that, if you can do those three problems right there, that's what you need to be able to do with pressures. Now, this is one of those things where we're just starting the unit. This is something that you need to be able to do, but this isn't the most important thing. What you're going to have is you're going to have problems later on which are more difficult, but during part of that process, I'm going to ask you to convert from millimeters of mercury to atmospheres, or from atmospheres to torrs, things like that. So this isn't super duper important, but at the same time, you have to be able to do it to solve some of the more difficult problems we're going to have later on. Okay, and then we've already talked about this one as well, but just a quick review in terms of temperature. There are 3 different temperature scales. One of them is Fahrenheit. That is not something that we discuss in this class. We don't use it in science at all. There is a way to convert between Fahrenheit and Celsius, but again, I'm never going to ask you about it, so don't worry about it. There is one of them, that is the Kelvin scale. We know that we use Kelvin in science. It is the same temperature increment as Celsius, so if you go up 1 in Kelvin, you also go up 1 in Celsius. And the nice thing about Kelvin is there is no negative numbers. The lowest temperature possible that you can get to is called absolute zero, and that is when you are at 0 Kelvin. There cannot be a number lower than that in terms of temperature. That means all energy is gone and you have nothing, you have no energy left. And then as we know, as we've learned already, to convert to or from Kelvin, these are some important ones here. The temperature in Kelvin is equal to the temperature in Celsius, and then you just add 273. To go backwards, we do the same thing. What we're going to take Kelvin minus 273. Okay, the Celsius scale we know is also used in science. Water freezes at 0. It boils at 100. The Fahrenheit scale, which we do use here in the United States, we don't use in science. Water freezes at 32, boils at 212. Again, you don't need to know that. Okay, so here are our temperature scales here. Notice that there is a 100-degree interval between the freezing point and the boiling point in Celsius and in Kelvin. And that, again, in Fahrenheit, it doesn't boil until 212, and it freezes at 32. Okay, so if we have 31 degrees Celsius, we want to convert that to Kelvin. We know that Kelvin equals the degrees Celsius plus 273. So 31 plus 273 is going to equal 304 Kelvin. So notice with significant figures, when you add, you're just looking at past the decimal point. Neither of these have anything past the decimal point, so your answer has nothing past the decimal point. So that is your correct answer, 304 Kelvin. Okay, and then if we had 75 Kelvin, we wanted to go back to Celsius. We know that Celsius equals Kelvin minus 273. So we're going to take our 75 Kelvin. We're going to subtract 273. So 75 minus 273 in Celsius would equal negative 198 degrees Celsius. And that is our final answer. So this is just a quick introduction to gases. Hopefully we talked about 4 different ways that gases are different from a solid and a liquid. We talked about what are the different units of pressure we use for gases. We talked about how you convert from one to the other, canceling out our units. And then we also talked about how you would convert between Kelvin and Celsius. If you are good with those three questions and you could answer all of them, then you have a good understanding of today's work.